Welcome to the shop. I'm continuing NQALHA Production Run 5 on my new Haas MiniMill 2 and having better and better days. Every day I work on it, it seems like I get a little better. I develop a few more procedures, checklists, habits, and I'm pretty much not making mistakes anymore, and things are going really, really smooth. Parts are coming out beautiful, and just in general, things are working really well. In previous videos, I talked about the difficulty in learning how to do scripting in the BobCad post processor, and well, I've got it under control. I'm a script master now, and I'm using scripting for a lot of different things, and I've got some ideas for using it for a lot more things. So right now, as I said in previous videos, the biggest limitation, the biggest software limitation of the Haas MiniMill is the tool changer, that it doesn't allow a large library of tools, say 60 tools or so, which is the size of my library. You can't load tool 41 into a 20 tool changer because the software is limited to 20 tool numbers. Fortunately, it's not limited to 20 tool offsets. The tool offset table has 200 possible tool offsets, and so I needed to come up with a way of telling the machine, okay, tool 41 is actually in slot 7. And at first I did this by writing a program in C++, a custom post processor that would figure out what tool set the tool was in. And then when I learned scripting in BobCad, it simplified things tremendously. So at the moment, I have a standard tool set of 14 tools that are always loaded in the tool changer, and then 8 different optional tool sets that I have listed on my sheet of tool sets. And then in the BobCad post processor and the custom user interface configuration, I can go into BobCad and say, oh, this part uses tool set 7, and it performs the necessary substitutions so that the tool number the tool number in the tool library only applies to the offset, and the script in the post processor that has the tables entered in it selects the appropriate pocket number. I've also come up with some other ideas as well to do in the BobCad array function. I can enter into the custom user interface the spacing when I'm using both the left and right side of the vise. I can enter the spacing between the left part and the right part, and it automatically, in the scripting function, automatically calculates the correct offset. And you know how much I like automation, because it's not just laziness. It's automation reduces mistakes. Anything that you can write a program, debug a program, and be confident that that program is now correct, that's one less place to make a mistake, one less thing to think about. And I haven't done this yet, but I'm cooking up a crazy idea now for doing work offset validation in the G code, because unlike a lot of shops where setup is rare and runs are long, my shop is exactly the opposite. Setup is frequent. I do many, many setups throughout the course of the project, and the run is usually pretty minimal. My normal run is 10 units. In this run, I'm doing 20. The biggest quantity that I make is drive rollers, and that's 160, but in general, I don't do very long runs, and I do lots of setups, and it's always easy to make a work offset mistake because sometimes Z0 is on the bottom of the part, on the ledge of the soft jaws, and other times it's on the top of the tooling plate. And if I forget to set the 0 on top of the tooling plate, well, I'm going to have a really bad day. So I'm actually considering, and I haven't done this yet, but I can imagine that by use of subprograms and the logic capability in G-code, that I can put in a validation that says, oh, this program uses Z0 on top of tooling plate, so check to see that Z0 is actually, within a few thousandths of the expected value, because I can't do an absolute check for, down to the 10th exactly what it is, because, oh well, the machine isn't perfect, the probe isn't perfect, and probably every time I put a tooling plate in, it's going to be off by a 10th or 2. But I think if I do some bracketing and some bounds checking, then I can have an extra piece of sanity checking going on here. So now, on to today's work. This is part of the new design for version 2.3, where all electronic devices produce heat. And in some cases, getting rid of the heat is really the limiting factor in the design of an electronic product, especially in microprocessors. Some of the limitations in processor speed and performance really are, well, how low can we make the power consumption and how can we get the heat out of the system? The NQALHA has 2 motor drivers on it, and these motor drivers are producing about 2 amps of current each. And even though the driver chip itself is based on field effect transistors that have a low on resistance, the driver still generates heat. And the driver is packaged, the little plastic package has what they call a power pad on the bottom of the package, and the intention is that you put a piece of copper on your circuit board that can draw the heat out of the plastic package and then solder that copper to the power pad. In the past, the design was to use the metal case that the circuit board goes into as the heat sink, and so I put the mounting screw very, very close to the motor drivers and provided a big thick trace of copper to get the heat through the power pad, into the copper, down into the screw, and then into the case. And this worked well, but then I had this crazy idea, well, what if I took it a step further and increased the contact area, changed the way the case was milled so that there was actually aluminum to aluminum contact between the bottom of the circuit board, where I have some vias going from the top surface of copper that's soldered onto the power pad, and then there's a number of vias drilled through the circuit board filled with solder. So now you have a path from power pad to copper to vias and solder to vias, and then that directly contacts with a thermal compound, directly contacts the aluminum in the case. And then I took it a step further and came up with a little machined piece of aluminum to go on top of the circuit board, touching the plastic case on top of the motor driver and transferring the heat with thermal paste into the cover. In the previous version of the cover, it was just a piece of 1/4-inch aluminum flat with a barely engraved logo. In the new version, I've managed to create you can see it there on the camera, managed to create a design that incorporates heatsink fins, fairly deep heatsink fins, deep and thin, into the cover, which is now 1/2 inch thick aluminum. And in order to do that, I have to cut a slightly bigger than 1/8 inch. I think it's 9/64 is the cutter I'm using. Slightly bigger than 1/8 inch groove in the aluminum. And it's 350 thousandths deep, which is a pretty darn deep slot. And of course, when you're doing slotting with a tiny little cutter, chip evacuation and cutter breaking is a real problem. And I haven't really pushed it to its limit yet, but I think I'm getting close, because the recommended feeds and speeds call for 1,000th per flute material removal and no more than 1 times the diameter of the cutter as the depth of cut, which is pretty much where I'm at right now. When I made these on the Tormach, I was limited to 5140 RPM. On the MiniMill, I've got the 10,000 RPM spindle, so I pretty much cut my cycle time in half. The old Tormach, let me look at the sheet here, 14 minutes and 28 seconds cycle time on the Tormach, and now I'm running 7 minutes and 19 seconds on the MiniMill. So it's still one of the longest cycle times in the project, but hey, it's a cool design. I like it. I actually validated with my thermal imaging camera. It helps a little bit. It doesn't make the thing run as cold as a stone, but it does help a little bit. And even though the controller gets hot and the stepper motors run hot just by their nature, just unavoidable, I haven't had overheating problems. The units don't fail in the field. The chips are thermally protected, so if they overheat, they won't destroy themselves. They just shut down. But I haven't had problems with people doing large pieces with lots of radiant heat coming off. The NQALHA runs hot and happy, and it doesn't appear to overheat and fail. So I've already run this program once, and it pretty much was the same as the Tormach toolpath. I just changed the speed to 10,000 RPM. So let's see if we can make this pig oink. (10,000 RPM). This is a 2-flute solid carbide end mill from Rushmore, USA, and taking 3 passes, slightly less than the diameter of the end mill per pass. And sounds good. Haven't broken a cutter. Seems to be working well. The pile of finished parts continues to grow. I'm nearing the end of aluminum part machining. I have a few steel parts to do. My flat plate steel parts are laser cut by the material supplier, and the only thing I need to do on the mill is drill some holes, do some countersink, tap some holes. That goes really fast. Then I gotta go over to the manual lathe and do the main horizontal arm axles. When I had the Tormach and the rapid turn, I could turn those in CNC on the rapid turn, and it's kind of humorous they call it rapid turn because it is slug slow. I mean slow. Because of the design of it, It's a CNC lathe attachment that mounts to the table of the Tormach mill, and then you mount to the non-rotating portion of the spindle a little wimpy little tool holder, a 0x0 size tool holder. I never even knew that they existed that tiny. And then mount a tiny little tool and cut really, really, really slow, because anything that is faster than really, really slow, you get chatter, you get bad things happen. So at least on my manual lathes, I can take a healthy depth of cut, get good chip breaking. It's a nice rigid manual lathe, and even though it's got a DRO, and even though I kind of have to pay attention for that last few thousandths and get out the micrometer and be kind of careful, I can rough them really quick on the manual lathe. So it's getting near the end of the process. Parts are coming out great. Deposits are coming in. Customers are waiting. Got to get this job done. So feeding it very close to 20 inches per minute, 10,000 RPM, chip load of 1,000th inch per tooth, and sounds good. Surface finish comes out beautiful. So far I've made 4 parts, and the cutter shows no signs of distress. I'm probably not going to try bumping it up anymore. I think I'm just going to say, you know, that's fast enough. I can't really, I mean, I could go from 3 passes down to 2 passes, but then that's, you know, 170 something thousandths, which is greater than the diameter of the end mill. And when I looked it up, the recommendation is no more than 1 times the diameter of the end mill, and some recommendations actually talk about no more than 50%. But hey, maybe that's for steel, maybe that's more conservative, I don't know, but I might just leave it like it is, figure out something to do while the machine is working away. I do have a combo toolpath set up here where I use the text editor to combine the first and second operation. The second operation is on the left vise on top of a tooling plate, where I cut the perimeter and kind of dig a little pocket in the back of the piece. The circuit board has pins, has a little 10-pin micro header that sticks out of the board that's used for programming with the JTAG adapter. A JTAG adapter is a piece of electronic hardware that allows the code to be loaded onto the processor, and the pins stick up just a tiny little bit above what would be the mating surface. And so I need to dig out a little bit of a pocket on the back of the part to provide clearance for that, and that's done in the same operation as milling the perimeter. So getting kind of close here. I really like the amount of coolant that the MiniMill puts out. Chip evacuation is probably the most important thing to keep under control when doing these deep, small slots, and the abundant amount of coolant seems to be doing its job. So now I'm watching as the machine pecks away at the mounting holes, 632 mounting holes. The one thing about this tool path that is slightly unoptimized, see that buildup on the counter bore? I might see if I can possibly modify the cycle, although as I'm saying that, the cutter cleared itself, so who knows, maybe I'll just leave it as it is. Okay, on to the 1/2" mill cutter, 3 flute Lakeshore carbide 1/2" solid carbide cutter running at 10,000 RPM, 90 inches per minute, which gives about 3/1000 per tooth, inches per tooth feed. And then I'm cutting out the pocket on the back, also at 90 inches per minute. And there we have it. So that concludes today's video. Things are going very, very well. The machine is performing very well. I've come up with workarounds for all of the limitations that I've found. Yeah, it's still got some just annoying pain in the ass stuff like wrong mode, but hey, that is a minor annoyance at best. All is well. MiniMill running great. Happy days in the shop. Thank you for watching. It's been fun.